Welcome to Saturdays at 7, Christian Scholars Review's conversation series with thought leaders about the academic vocation and the relationship that vocation shares with the church. My name is Todd Ream. I have the privilege of serving as the publisher for Christian Scholars Review and as the host for Saturdays at 7. I also have the privilege of serving on the faculty and the administration at Indiana Wesleyan University. Our guest is Mark Behrens, the John and Margaret McAndrews Professor of Mathematics at the University of Notre Dame. Thank you for joining us.
Hi, thank you.
I'd like to open our conversation by asking about a 1960 article by Eugene Wigner. For audience members unfamiliar with Wigner, he served most of his career on the faculty at Princeton University, served briefly as the director of research and development at what became the Oak Ridge National Laboratory, and won the Nobel Prize in Physics in 1963 for his contributions to the understanding of the atomic nucleus. In February 1960, he published The Unreasonable Effectiveness of Mathematics and the Natural Sciences in Communications and Pure and Applied Mathematics. When reading this article, I found Wigner resorting to curious and inviting forms of language. For example, in his first 2 points, Wigner claims the enormous usefulness of mathematics and the natural sciences is something bordering on the mysterious, and there's no rational explanation for it. In his second of 2 points, he then contends it's just this uncanny usefulness of mathematical concepts that raises the questions of our physical theories. To begin our conversation, I wanted to ask you, how prone are mathematicians and physicists to using terms such as mysterious and uncanny in summations of their efforts?
I think we use that terminology a lot, but I think in a way that's different from the way that Wigner is maybe talking about it in his article. I mean, in the article, it seems to me like he's suggesting that it's mysterious or strange that we can describe the laws of nature with mathematics, like that mathematics is the right language or the right framework in which to describe these laws. But I don't think that, I mean, obviously everyone has a different relationship with their way of thinking about it. I don't find that aspect mysterious at all, because to me, math is just logic. Like, and if you're, applying logic to understand behavior, predictable behavior of nature, that's just what you're doing. So naturally, it's, and you're using quantitative techniques oftentimes. So naturally, mathematics is going to be the way in which these things get expressed. Yeah. That's not mysterious to me. But we do use the term mysterious a lot because a lot of times what we do is we're discovering different things that are true, like proving theorems, discovering different mathematical truisms. And all of these discoveries proceed through logical deduction. So they themselves aren't mysterious from the point of view that you've already shown them to be via via logical deduction. What's mysterious is when you find a connection between two things that you didn't expect. And so that's where we'll often use the term mysterious. Or maybe we'll observe in a bunch of examples a phenomenon that appears to always happen, or maybe in many different contexts, but we can't yet find a framework that explains that. And so then we'll call it mysterious, even though we know it to happen.
Despite his command for math and physics, in what ways do you think Wigner resorts to making such observations, perhaps due to his inability to draw upon other ways of knowing, to draw from perhaps other academic disciplines that may be able to offer him resources?
It's kind of weird. I mean, like it in my mind, math is sort of tautologically the right way to approach the questions of describing laws of nature. And so, from that point of view, it's like, okay, well, why would you take something that's so perfectly adapted and swap it out with something that maybe isn't? Wigner seems to be suggesting in his article that, or, be worrying that maybe there's another way, another language, or another framework to understand nature that we've never thought to use, I don't know. Like, to me, it's sort of tautological that math is the language because it's just logic and deduction. But I think that what other disciplines can offer, say a physicist or a mathematician, are different perspectives that might cause them to define or think of new things that they didn't think of. Like a mathematician, they could only study the concepts that they first come up with. Like, we have to first define an object and then we can study it, right? But we might have not thought to make a definition. We might not thought, to study. And so, that's where other disciplines come in. I mean, as a mathematician, it's very common for concepts to come up in physics that we never thought about. And then it's like, oh, let's make a mathematical framework and study that mathematical framework. We do that all the time. I think philosophy, I think religion, I think theology, I think all different disciplines have different things they might come across that you might have not realized is a thing. And then it might inspire you to create something that you've never created before as a result.
Yeah. In what ways, if any, is mathematics perhaps an expression of the academic vocation defined by persistence in the pursuit of truth through that which is otherwise mysterious, uncanny, or at least for a season, scholars think may not offer any particular rational explanation? Is mathematics defined by that working through those details to perhaps come out the other side?
I think in some sense, yeah. I mean, in the sense of mathematics, is meant to, like, say there's a phenomenon that's mysterious, right? And then the goal of a mathematician would be to explain that phenomenon through a mathematical framework, through a series of deductions, and therefore make it not mysterious, right? To say, okay, it happens because of this. That's I feel like what our job is.
Yeah. Thank you. I want to ask you a couple of questions now about your own journey with mathematics. And it started with mathematics and physics, actually, as an undergraduate. You were a double major at the University of Alabama, earned a master's in mathematics, again from Alabama, but then a doctorate in mathematics from the University of Chicago. At what point did you sense that mathematics would prove central to your sense of vocation?
I sort of chose physics kind of randomly. I was originally wanting to be a musician, and then feeling like I wouldn't make it. Then thought, read a book about physics and it sounded interesting, and so I went into that. But in the process of doing physics, you have to learn a lot of mathematics, and I quickly realized the precision of mathematics, the sort of absolute knowing of certain things, and sort of the defining objects very carefully so that you know what you're talking about, was very appealing to me. But it also was, there's no way I would have gone down this path without many mentors that, just spent hours and hours of their time helping me out, So they helped, like, I got interested in this, but it was through their encouragement and through all their work that made it actually successful for me.
Yeah. Are there any individuals and or experiences with those individuals that you would note that proved more formative than perhaps others in terms of your vocation?
I mean, even, like my later algebra teacher, Martin Dixon, he gave me my first kind of formal mathematics course with proofs and mathematical rigor. And I had no idea what was going on at first. And, by the end of the class, I was loving it, and at the end of the class, he asked me, have you ever thought about becoming a math major? And I had not, right? But I never would have thought that had he not said that, right? So I think sometimes, just for somebody to alert people that that's a possibility.
Yeah.
That's something. And then Alan Hopperwasser was another professor there who took me under his wing and did some mathematical readings with me. I worked with years with another mathematician, Bruce Trace, and then another professor there, Norihiko Minami, got me into my current subject that I do. All these people meeting with me every week, sometimes for hours, that's a lot of time. And that's, that I think that's extremely valuable.
Yeah. Thank you. You began your career by serving as a postdoc and then tenure track faculty member in mathematics at MIT. And along the way, you served as a visiting professor at Harvard University and then more recently at Northwestern University. How did those experiences or commitments shape your sort of research efforts and your focus?
When I came to MIT, there was a lot beginning to happen, and a lot unfolded while I was there in terms of a lot of research directions in my subject that have, I mean, a lot of activity has been going on in terms of solving big problems in my subject in the past several years, and a lot of that seemed to start to begin while I was there. Other people were there doing this stuff. And so it was kind of like coming to like ground zero at this, very exciting time and seeing all these
Yeah.
new ideas gestate and come forth. So that was a huge influence for me. And,
Yeah.
in general, just being around other people doing, coming up with amazing new ideas, they help you come up with new ideas. And, it's inspiring.
Yeah. How did those experiences also shape your commitment, say, to teaching and then to service both beyond and on your campus?
I mean, in terms of teaching, I mean, at MIT, I didn't really have to think too much about teaching because the MIT students are kind of intense and crazy in a certain way, So like they're the only students I've ever met who might complain the homework was too easy or there wasn't enough homework, it's sort of so I never really worried about what I kind of threw at them. But in other contexts, I did worry, like I thought, okay, like I'm teaching a calculus class, these are freshmen, a lot of them probably don't want to take this class, they probably dislike mathematics. How can I make this bitter pill easier to swallow, But lately I've been rethinking that. I've been thinking instead that actually maybe diluting it is not the way to go. Like maybe instead the way to go is try to convey why, to go full in and then explain why is this, interesting. Like you're coming to a university to, all your different classes, you're experiencing ideas and things that you never experienced before. Why shouldn't your math class be any different? It should be just as transformative as your first philosophy class.
Yeah.
And so I'm trying to be more authentic in my undergraduate teaching.
Yeah.
In terms of service, I think a lot about all of those mentors that helped me over the years, and I see if I can perhaps imitate or give back or do what they did for other people, that want to follow this path.
Yeah. In 2014, then you accepted an appointment at the University of Notre Dame. What led you to accept that appointment? And in what ways maybe have these sensibilities in terms of research, teaching, and service changed over the course of now the 11 years you've been in South Bend?
I mean, I guess for Notre Dame, I was on the job market, and I had different possibilities. And at the time, Notre Dame had introduced an initiative to greatly enhance their topology program, and it just seemed like a great opportunity to get in right at the time when they were going to do this rebuild and then augment this group. And so that was very appealing to me. Another thing was I was just beginning to re-engage with my Catholic faith. My child had been born in 2012. So my first child came in my life as a stepson, and he already kind of grew up in the church in the church, as it were. And so I never was really sort of concerned about him knowing anything about what faith is. I don't care what my kids do in terms of faith, but I want them to have an idea of what faith is, as opposed to not have any idea.
Yeah.
And so I wanted to have some context for my daughter. But, because I went to the only framework that I personally knew, which was Catholicism. And
Mhm.
so I had enrolled in an RCIA there. And, and so in that reengagement, then the idea of going to an institution that was linked with this was kind of appealing to me as well,
Mhm.
because I was really inspired by the conversations that I was having with the retired priest that was running that. And then, frankly, my wife also, in terms of the various options, she told me, like, based on what Notre Dame was doing, she's like, you have to go there because this is going to be the best place for your research. And I always
Mhm.
listen to my wife.
That's smart on multiple levels, I would say, at least from my personal experience. In what way, since coming to Notre Dame, have you been able to take advantage of the insights and wisdom that are housed within other disciplines or by faculty colleagues, not only just within mathematics, but also beyond mathematics?
I mean, in some sense, I feel like I could do more in that regard. There are people, that I know have connections with the physics department or have
Yeah.
connections with the philosophy department, and I'm not one of those people. And but sometimes it's just lack of time.
Yeah.
There's only so many hours in the week.
Yeah.
You have enough weekly meetings, and you have to find time for your research and your teaching, and before you know it, I do find that sometimes they'll have events, they'll have like lectures and things like that are really enriching and thought provoking, and so I feel like just being on a campus that brings in a lot of these activities, can also fulfill that role.
Yeah. Thank you. Want to ask you now about your area of expertise. You mentioned topology, and that's
Mhm.
part of what led you in terms of the University of Notre Dame's investment in its topology area within mathematics. For individuals who are unfamiliar with topology, how would you define it?
So basically, it's a study of higher dimensional shapes. So you can ask, what are all the different surfaces that you can
Mm,
create? Now, for a topologist, we say two surfaces are the same if you can deform one into the other. So for us, like a cube and a sphere are the same object, because if you think about that cube as being like made of rubber and inflate it with air, it'll eventually kind of turn into a ball. So for us, those two are the same, but a donut is distinctly different because no matter how you twist that donut, or deform it, it will never turn into a sphere because it'll always have that hole in it.
okay.
So those are like two-dimensional shapes sitting in three-dimensional space, but we're interested in n-dimensional shapes, perhaps sitting in m-dimensional space, or maybe not sitting in any space at all, right? And it's reasonable to ask, well, why should you care? I mean, we live in a three-dimensional universe, four if you count time, but we don't know what the shape of the universe is. How can we even answer that question if we don't even know what four-dimensional shapes are possible?
Mm, yeah. Thank you. Of all the subdisciplines within mathematics, then, what drew you to the study of topology?
I started off in analysis, which is like calculus, basically.
Hmm.
Just a fancier version. But I was really interested in the idea of doing integration on these shapes, and so they would call them manifolds. And so then that got me interested into it. Got me into what we call differential geometry. And then I realized that the aspects of differential geometry I found the most interesting were those aspects where they didn't change if you change the shape.
Yeah.
And, if you deform the shape, that is to say. And so this then becomes topological questions. And so I sort
Yeah.
of realized this was what I found most interesting.
Yeah. In what ways, if any, might the study of topology lead to conclusions, or at least initial conclusions, that are mysterious, uncanny, or for which no rational explanation may yet exist?
So I think, I mean, like sometimes we might do what we would call computations, where we
Mhm.
might like see, all the different examples of a different phenomenon happening in a different dimension or something like that. But then we don't have an explanation for why that, like you could do the computation. In that sense, it's not mysterious. You did the computation. It's
Yeah.
logic. I mean, that's the thing about mathematics. It doesn't have contradictions. That's what's different about mathematics than just about any other thing. It doesn't have contradictions by its nature. If there's a contradiction, that means that you made a mistake. There was a human mistake somewhere, right? That
Yep.
so it's there because you've got your deduction that says it's there. But maybe you don't, but maybe you're seeing a phenomenon that you can't explain why that pattern is there, And so then that's the mystery, and that's what we encounter all the time.
Yeah.
It's kind of like how a physicist does experiments, sees a phenomenon, and then wants to come up with a theoretical framework to explain that phenomenon they witness in their experiments. It's the same thing.
Yeah. Would you describe for us one of your recent research efforts and what drew you to it and how you came about to frame it?
I've got a paper I put out recently with a postdoc named Jack Carlisle, where we study something called equivariant periodicity. So equivariant is basically the study of things with symmetry, and we're thinking about very simple symmetries like maybe things where with a flip symmetry, like if you take them and flip them, they're the same, or things that if you maybe rotate them by a quarter, each time, then they're symmetric. So something like that, right? And so equivariant topology is the study of shapes with symmetry. Okay. And so you could take any question that you would normally ask in topology and ask, okay, what if we add a certain symmetry to it? Then how does that change this question? So the thing that I specialize in are what are called homotopy groups, specifically homotopy groups of spheres. So what these are the different ways to wrap a high dimensional sphere around a low dimensional sphere, which might seem like a sort of weird thing. Like, why would you want to do that? But it turns out that every single one of these shapes that I described, these higher dimensional shapes, is built by taking a higher dimensional ball whose boundary is a sphere and gluing that boundary along another shape and doing this iteratively. And so basically you have to know how to wrap these higher dimensional spheres, which are boundaries of higher dimensional balls, around other spheres in order to know what the structure of these geometric shapes are. So that's why we do that.
And I would assume that there may be considerable applications for such thinking in areas, not only physics, but also engineering.
It's kind of funny. I don't really think too much about the applications, to be honest with you, but that doesn't mean they don't happen. I mean, they do, and I'm often surprised when they do, but it's not sort of, oftentimes I'm oblivious by them, and it doesn't, in some ways, it doesn't motivate me very much. Maybe that sounds weird. I mean, like for me, I think that there's questions that are natural, and interesting to ask.
Yeah.
And then you ask them and try to find the answer, and then there sits a repository of answers to natural questions. So when somebody in another subject asks this question, they be like, well, this sounds like something a mathematician would have thought of. And if we have the answer waiting for them, then we've done our job.
Yeah. So along those lines, then, in terms of the particular project that you and Jack recently pursued, what did the two of you find that was sort of intrinsically appealing or gratifying in the pursuit of that effort?
So one of the things that happens, one of these sort of mysterious things that you might call it, that happens in these in the regular homotopy groups of spheres, the non-equivariant, the ones without symmetry, is that it turns out that there are certain patterns in the ways these things wrap, in these homotopy groups across many dimensions, and the dimensions are repeated with a fixed period.
Yeah.
Okay. And so like maybe an 8-fold periodic pattern emerges, or a 192 periodic pattern amongst dimensions. Like it may be weird to think, okay, we're studying dimensions every 192. Like what the heck, So we're studying hundreds of dimensions. That's what we're doing. Okay. So this is this periodicity or chromatic behavior that I'm speaking of. So what we were looking for that equivariantly, and there was many other things that many people have done in this direction, and we were sort of building on their work. And so one of the things that I studied in my thesis was this thing called the Mohold invariant, which was a transformation that took one kind of periodicity to another periodicity in the homotopy groups of spheres. And this construction itself, people have observed that it can be made from one of these equivariant or symmetry kinds of perspectives. And what we discovered was that the equivariant periodicity explain the connections between the periodicities in the input and the output of this invariant. So to me, that was like great. That was really interesting.
Yeah. Yeah. Thank you. You've served as the editor for several journals and presently serve as the editor for Geometry and Topology. As an editor and a prominent scholar in your field, what advances in topology have you witnessed over the course of your career?
I mean, a heck of a lot. I mean, our whole, it seems as if things are just always happening and changing. Yeah, our whole sort of language that we've been using to express our results was revolutionized by this mathematician Jacob Lurie, who really turned the subject towards thinking about these things called infinity categories as a different kind of operating system to work in, and that seems to really be taking hold and doing amazing things. There was these equivariant techniques that I was speaking of really came back into the forefront after many years of sort of not being widely considered when Hill, Hawkins, and Ravenel solved this long-standing problem, like this 50-year-old problem called the covariant invariant problem, which was about what dimensions certain manifolds could have certain properties, and they did it using these equivariant techniques. So that was interesting. And very recently, there was another long-standing problem about this periodicity phenomenon that I speak of, called the telescope conjecture, which is really a question about whether there can exist certain periodic families that are almost undetectable, a kind of a dark matter in our periodic homotopy groups. It was something we never actually witnessed in our computations, but knew theoretically could be there. They proved that, in fact, it's there, and most of the groups out there are predominated by this dark matter. So that's a fascinating discovery. And now we have to go out and see if we can actually detect it and see it in our computations.
Yeah. So there's no shortage of activity going on and no shortage of possible topics moving forward then, I would assume.
No, it just multiplies and multiplies. It's almost hard to keep up with.
Yeah, that's great. As we turn toward the end of our conversation, I want to ask you, as a mathematician and topologist, qualities and or characteristics define your understanding of the academic vocation. And in what ways have those qualities perhaps maybe even changed over the course of your career from when you started at MIT to where you are today?
I mean, definitely, when I first started out, I was just trying to, get a career going. It was just, it was just like, okay, how can I, get my foot in the door? How can I make this a successful career? How can I get a job? How can I make sure, how can I get tenure? These are pretty practical questions, and this was sort of, things that were driving me in addition to just my interest in the subject, right? Now, I think a little more. I feel like I think a little more with a lot more perspective. Both realizing the privilege and the gratitude that I have for being able to do this as a career, this thing that I love, and interact with other people that do it. That's just great. But also thinking about how can I help other people that are trying to follow this path. How can I use my perspective? How can I use my learned experiences to help them on this, very difficult and challenging path?
What virtues then, whether they be intellectual virtues, moral virtues, or theological virtues, do you believe are most important to cultivate as a mathematician and perhaps also as a topologist in terms of one's ability to succeed and flourish in those fields?
I think the virtue of openness, of open knowledge, of open, I think there's a lot of tendency to want to carefully guard the things that you learn or discover, that you might be worried, okay, other people are going to, if they have this, then they might sort of jump ahead of me or something. To think more about your position in the race, as it were, rather than our collective knowledge, as humankind of mathematics and sort of what we know and what we can know. When we work together, when we share our ideas openly, then we're going to move much faster to answer these questions. We can make discoveries much more quickly by working together and just forgetting about the idea of personal glory or personal gain. If we just, put all our cards on the table and tell everybody everything we know, that's a virtue that can help the subject.
Yeah. In other ask a related question here. In other fields within the natural sciences, but also in the social sciences, and to some extent even in the humanities now, we're seeing more and more people working in teams and working together on problems. Is that beginning to, you talked about your work, say, with Jack Carlisle, who's a graduate student with
He's a postdoc. Yeah.
postdoc.
Yeah.
Is that becoming more and more common?
Oh, yeah. Yeah, no, that's another way in which the subject has changed a lot since that.
Yeah.
I mean, when I was just graduating, it seemed to be very common. I mean, collaborations always have happened through history, but it's very common to just write papers just by yourself or work on projects just by yourself. Mathematics was largely a solitary game, and that's just transformed in the past few decades, like the past couple decades. It's just now it's like a team sport. It almost seems as if it's very rare for problems to be solved by one individual. Rather, it's usually a team of people. And usually you've got a problem, you put together a team to solve the problem. Improvements in communication, like look at us talking by video from two different places. I mean, the fact that we can do that revolutionizes these possibilities.
In your estimation, have tenure and promotion processes then kept up with those changes to honor and recognize the validity of contributions that are done in collaborative contexts, say solitary or individual contexts?
I mean, in my subject, the answer is definitely yes. I mean, like say, okay, people, it's a collaborative game now, everybody recognizes that. Nobody's going to see that most of your papers are collaborations, that shouldn't count. It's probably all your papers are collaborations.
The flip side of the question in relation to virtues, then, are there any particular vices that you believe it's important for mathematicians to be vigilant against that can creep in and cloud perspective or pose challenges to a proper understanding of the vocation?
I think the thing I mentioned about, about people maybe getting too worried about the person or as opposed to the math, I think that's a vice. I think that's a danger. I think competition can be healthy in the sense, like sometimes it can help you bring your A game, to feel a little competition, but it can also be destructive. It has to be very careful to keep it healthy and not allow you to do anything that would jeopardize the integrity of what you're doing. I mean, it really is a sacred honor to be able to study this sort of fundamental problems of thought. And that's what we're here to do. So, that I think it's important to keep that in mind.
Yeah. As we get ready to close our conversation, I want to ask you if they're about mathematics and its impact in other areas, fields beyond mathematics, and what that could look like. What contributions do you believe mathematics is uniquely positioned to make to colleagues who are called to serve in other disciplines?
I mean, we have a way of thinking. I mean, as I mentioned, we have this luxury that our objects are so well defined that contradictions aren't then a matter of debate. They mean, okay, somebody made a mistake, right? Almost no other subject has that, but it causes us to think in a certain way that I think is different from certain subjects. It's a kind of like extreme logic of some kind, And I think that kind of mathematical thinking, or that sort of this sort of idea of trying to make your ideas very precise. I think that kind of thinking translates into other disciplines, even when the discipline it's inappropriate to expect that there is that level of precision is possible. It still gives you like the idea that you could think in these terms is a different way of thinking. And so I think that, I mean, mathematicians, it's very common for mathematicians to go off into other disciplines, right? And I think that they bring with them a different way of thinking that other people enjoy and find interesting, or people that even study math as part of, and end up doing something different, or just to get exposed to mathematical thinking and do something different. I think that kind of mathematical thinking can give them a different way of approaching their problems, So I think we have a lot to offer in that respect.
Yeah. In what ways can colleagues in these other disciplines become more aware of the contributions that mathematicians can make, become more receptive, and even make more use of those contributions?
I mean, maybe it goes on both ends, right? Like maybe we as mathematicians need to be able to engage better with people in other disciplines and be able to convey our ideas, in ways that are understandable and can be received. Then, of course, other disciplines then probably should realize that mathematics can be a very valuable tool. I think economics and in pretty much any science and biology, in many different areas, the idea that mathematics can help your subject has taken hold, that we have something to offer that when you apply it to your problems could give you surprising results.
Yeah. To close then, I want to ask, these kinds of contributions that we're talking about, in what ways do you think they can be of benefit to the church? And can the church become more aware of them and make more use of them moving forward as it thinks about its engagement with the world?
I guess there's several layers to this, right? I mean, like one is, I've talked about like the mathematical way of thinking, and then there's what mathematics actually can do, for a subject, right? From my personal point of view, what I'm not saying is take every word in the Bible and make logical deductions from that. I think that is very damaging. I think that things need to be put into context and layers of meaning need to be applied as people do so well. I think that maybe our perspectives on problems, maybe that kind of perspective can be ported beneficially to other areas, including the church.
Yeah, those habits of mind, so to say.
Exactly. Yes.
Yep. Thank you. Our guest has been Mark Behrens, the John and Margaret McAndrews Professor of Mathematics at the University of Notre Dame. Thank you for taking the time to share your insights and wisdom with us.
Well, thank you. I appreciate it.
Thank you for joining us for Saturdays at 7. Christian Scholars Review's conversation series with thought leaders about the academic vocation and the relationship that vocation shares with the church. We invite you to join us again next week for Saturdays at 7.